time for us to do some problems involving sequences, which another way we can think of it is list of numbers, and looking at what can we say about these, how do we generate them, and how do we gain intuition. Of course, the answer to the last question about how we gain intuition is practice. The more that we practice, the more intuitive things will become, and the better we are at solving problems. So, do as much as you can on your own. If you see a problem, use the pause button and try it out by yourself first. And if you do need my help, okay, unpause, and then we can work it out together. Well, let's begin. Our first problem. We're given A0, so the zeroth term, we often start with 0, but we can start anywhere, is some number, 137. And A sub n is n minus 18 times A sub n minus 1 plus 3. Find A sub 20. Now, what we see here, this is an example of what we would call recursive. Because what happens, if it says, look, if I want to know a particular value in my sequence, an entry in my list, I really look at the previous entry and modify it in some way. So that's the idea of recursive. It says, look, if I want to know this value here, you look at previous values that came before it and say, how can you modify it to get there? So, what does that tell us? Well, one way we could approach it is to say, look, we know where we start. We start at A0. We could say, all right, we'll find A0, A1, A2, A3, A4, and eventually we'll go to A20. Now we have to be patient if we do it that way, but it will work, right? It's pretty straightforward. So let's see. A0, 137, right? Because that's given to us. According to the rule, A1 is what? Well, this is n equals 1. So put an n equals 1 over here. So you would have 1 minus 18, A0 plus 3. Okay, so that's negative 17 times 137 plus 3, which does not look like a number we want to compute. I guess we could pull out calculators, but that kind of defeats the spirit of what we're trying to do, right? We're trying to say, well, what if we didn't have calculators? Now, what would A2 be? Well, A2, okay, so that would be, see here, it's n equals 2. So you plug in n equals 2 over here, and you would get 2 minus 18 times A1. 2 minus 1 is 1, plus 3. Okay, well, 2 minus 18, that's negative 16 times negative 17 times 137 plus 3 and plus 3. And that is just copied from above. And wow, so 16 times 17 times 137. Okay, all right. Maybe we should pause and start thinking there's got to be something here. Because they don't want to ask us a problem just for busy work, would they? I hope not. So let's think about what's going on. Now, remember the classic mantra. And what's the classic mantra? So, 0 is a friend. Now, of course, what does that mean? Well, this is sort of a spoiler. Well, how can we make progress? Notice this n minus 18. What's going to happen to that? Well, it changes based off of n. And so you can say, well, what's a nice value for n? If I'm looking at n minus 18, well, going back to the 0 is a friend, let's jump and say, okay, let's look at n equals 18 and see what we can say. All right, it would be a sub 18 equals 18 minus 18 times a sub 18 minus 1, that's a sub 17 plus 3. Now, you might say, too bad we don't know what A17 is. It doesn't matter what A17 is, because 18 minus 18 is 0, and 0 times anything is 0. So this becomes 3. So A17 is undoubtedly a really horrendously big number. It would probably, if we were writing it down, take the length of this page here. Huge, huge number. But when we go to A18, whoosh, collapses. And the nice thing about 18, we're close to 20. All right, so what about A19? Okay, so n equals 19. That would be 19 minus 18 times A18 plus 3. Well, 19 minus 18 is 1. And then we're going to times it by the previous term, 3. And we're going to add to that 3. So 3 plus 3, 6. And A20, which is what we want, what is that? Well, 20 minus 18 times the previous A19, right? 20 minus 18, A sub 19, plus 3. So that's 2. 20 minus 18. The previous term is 6. Add 3, and we get 15. Good. Done. We got an answer, and it's actually not a bad answer. It's a kind of a nice answer, the answer that we'd be happy to take home to meet our family. So what happened here? Well, the thing is, you feel, I've got to start at the beginning and I got to work my way up. You would absolutely get the right answer if you did it that way. But boy, you would feel frustrated when you got to A18 and say, I should have seen that earlier. So oftentimes it helps. Say, look, before I jump into a problem, let's step back and say, maybe there's a better way. Maybe I can make life easier on myself. Yeah, I think you can. It happens quite a lot. All right, on to our next problem. So, here we go. A sub n is defined as 1 plus minus 1 to the n over 2. And that's for n equals 0, 1, 2, ... What can we say about our limit as n goes to infinity of a sub n? Okay, well, let's think about it. All right, so we have our, we can make it, n, and is 0. Well, minus 1 to the 0 is plus 1. 1 plus 1 over 2 is 1. N equals 1. Minus 1 to the 1 is minus 1. 1 plus minus 1 over 2 is 0 over 2, it's 0. N equals 2. Minus 1 squared is 1 again. 1 plus 1 over 2 is 1. And what we see, I think we see a pattern going here. See, minus 1 to an even is going to be plus 1, which ends up with 1 plus 1 over 2. Minus 1 to an odd is minus 1. 1 minus 1 over 2. So what's going to happen is we're going to alternate. So it's 1, 0, 1, 0, and just going to keep doing that. All right, so our sequence could be described as we go back and forth 1, 0, 1, 0, 1, 0. If we think about it in terms of the line, what do we have? Well, we have our 2 points at 1 and at 0. And our sequence says just hop back and forth. Doom, doom, doo, 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 doom, doom, doo, doom, 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 doo, doo, doo. It's just going back and forth. Now, our question is, what can we say about our limit as we go to infinity? Now, when we're looking for a limit, the real question is, what are we getting close to? Now, the answer might be nothing at all, but when we think about limits, the question is, what am I approaching? What am I getting close to? And it seems like you could say, well, the natural candidates are 0 or 1. But the thing is, I have to get close to one value. A limit can't be getting close to 2 different numbers simultaneously. Because if I have 2 different numbers, there's always a gap between them. And so I can't be close to this number and be close to that number as well. So, what's our conclusion? Well, our conclusion is this does not exist. It's an example of a limit which doesn't converge. And how do we argue it? Well, we've already said the basic idea. We could go into more technical arguments and say, look, we know if there were a limit, because we have a lot of points close to 1, we'd have to be close to 1 here. But we'd also have to be close to 0 at the same time. And so ultimately what it comes down to is you cannot simultaneously be close to 0 and 1. So the limit does not exist. And that happens a lot. Sequences, they don't always work so nicely. It just depends. Of course, we'll see other examples of sequences which do work pretty nicely, so who knows. Okay, our next problem. Write down the first 5 terms of the following sequences. Just some practice here. So this is not so bad. All right, well, let's start with the first one. So this is not really, it's more just mechanical here, and we'll make some observations perhaps as things come up. So note, it tells us where to start. So we start at 0. And by the way, you don't have to use the symbol n. You can use any symbol you want. N is very common, K, J. The symbols that are often used for indexing tend to be in the middle of the alphabet. All right, so what do we do? Well, we start where it tells us to start. We start at 0. Minus 1 to the 0 is 1. Minus 1 to the 1, minus 1. Minus 1 squared, 1. Minus 1 to the third, minus 1. Minus 1 to the fourth, 1. And that's the first 5 terms. Now remember, it's going to keep going, but I only needed the first 5 terms. All right, well, next one. Okay, 2n. And note here, where do we start? We start at 3. Okay, so what do? Well, start 2 times 3, 6. 2 times 4, 8. 2 times 5, 10. 2 times, where are we up to? 6. 12. 2 times 7, 14. And there we go. So our sequence starts 6, 8, 10, 6, 8, 10, 12, 14. All right. Okay, how about our next one? 2n plus 6. And here, we're going to start at 0. Okay, so 2 times 0 plus 6, 6. 2 times 1 plus 6, 8. 2 times 2 plus 6, 10. 2 times 3 plus 6, 12. Whoops, 12. 2 times 4 plus 6, 14. Okay, now, there you go. Let's pause. What do you notice? You notice something here, right? I hope you see it. Look, these two are the same as terms of list. So it's the same list of numbers. Indeed, the only thing that's happened is that the index where we start has been shifted. So what can we think of happening here? Because there is something that we want to sort of foreshadow of things to come. And what have we essentially done is we've done a shift. Now, how do we think of shifts? And a nice way to think of a shift is you can really think of it as a change of index, and we have another name for it, and we can call that substitution. In other words, we're just shifting things around, it's really substituting one index for another index. So we'll see this type of idea later on as we get into not just looking at sequences, but starting to add things up. In other words, sums. Okay, well, 2n, n equals 0 to infinity. Okay, now notice this was also 2n. What's the difference? Where do you start? So 0 is 2 times 0, 2 times 1, 2 times 2, 2 times 3, 2 times 4. And there's 5 terms, so we're done. All right, the last one. Okay, 2 to the n over n squared. And we start at 1. Good thing we don't start at 0, because then we have something divided by 0. Uh-oh. But here, we're starting at 1. Life is good. And, well, just start working the terms, right? N equals 1. 2 to the 1 over 1 squared. So we can write that as, well, we can even just leave it as 2 to the 1 over 1 squared. Then 2 to the 2 over 2 squared. And 2 to the 3 over 3 squared. And 2 to the 4 over 4 squared. And 2 to the 5 over 5 squared. There's the first 5 terms. You could have simplified. You could have said, oh, well, that's the same as 2 over 1 is 2. 2 squared over 2 squared is 1. All right. Then you have 8 over 9. All right, 8 ninths. Then you have 16 over 16, which is 1. Then you have 32 over 25. Now, you might say, okay, which one is better? And the answer is they're both answers. So I don't want to say, oh, this one is better than that one. It depends what you're trying to do. If you're just saying, look, I just want the numbers in simplest form because I want to save ink and make things look pretty at the end, then maybe the second way where we simplify everything. However, if we're looking for patterns, there's a danger in simplification. The danger of simplification is things like you get cancellation of terms and you obfuscate the pattern. So you have to be careful. There's always that sort of balancing act you have to do. Am I looking for a pattern? If you are, hold off a bit before you jump in and start canceling terms and simplifying. It often pays to not simplify so you can see how things are fitting together. And again, we'll probably see some examples of this as we go on. There's so much good stuff waiting for us. This is going to be such a wonderful part of the course. All right, good. Well, let's keep going. More problems. Given a0 is 1, and a sub n is the square root of 1 plus a sub n minus 1 is a sequence. Okay, because it defines things, right? I know where to start. I start at 1, and then I know how to keep simplifying. And it's a sequence which converges. You don't have to prove it. What's the limit? Okay. Now, this is interesting. We'll get into why the answer is interesting at the end. But let's suppose we think about it. So what does it look like? So the first term is 1. The second term, that would be a(n), where we put in n equals 1. It's the square root of 1 plus 1. So the square root of 1 plus 1, which we could write as square root 2, but I'm going to leave it as square root of 1 plus 1. The next term says what? Take the square root of 1 plus the square root of the previous term. Term after that will be the square root of 1 plus the previous term, which is the square root of 1 plus the square root of 1 plus 1. And so you can imagine if you kept going, dot, 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 you get the square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of 1, It's like we have this infinitely long nested of square root of 1s. You're like, whoa, what is that doing? What is that doing? Okay, so here's the thing. We know it's a sequence which converges. What does that say? Well, it says, look, the limit as n tends to infinity of a sub n equals something. That's what it means to converge. The limit approaches a value. Okay, so that's a given. We know that the limit exists. Okay, so now we're going to turn that and use it to our advantage. Okay, what do we do? Well, let's think of our two sides. So an is the square root of 1 plus a sub n minus 1. Now, let's take the limit of both sides. So we'll start with the a sub n. What does that go to? Well, this is going towards L. How do I know that? Because it says it right here. Limit as n goes to infinity of a sub n is L. What is this side going to? Well, the square root, it's a continuous function, so you can pass the limit in. And now we can say, well, what's true about this a sub n minus 1? We know that a sub n goes to L. What does a subscript n minus 1 do? What does it go to? All right. Can you see it? So we're starting at 0, keep going, and so what happens is if I look at a term far down, so I've gone a ways that way, here's my a sub n, what's the conclusion? It's close to L because I'm going to L. Where is a sub n minus 1? It's right next to it. So if all the terms are getting close to L, then if I just shift over by 1, I'm still getting close to L. So the key here is that this also gets close to L. So that's going to the square root of 1 plus L. So whatever the limit is, it has to satisfy that that value is the square root of 1 plus itself. And now it's like, okay, great. I don't even have to worry about sequences anymore. This is now an algebra problem. The question becomes, which number is equal to the square root of 1 plus itself? Well, okay, so we square both sides because I don't like dealing with square roots. L squared equals 1 plus L. And then we say what? Well, let's put everything over. L squared minus L minus 1 equals 0. And does it factor? Does it? I don't think so. See, the problem is you have to find two things that multiply together to give you negative 1. Only one way to do that, positive 1 and negative 1. They don't add up to minus 1, they add up to 0. So it doesn't factor. But we can still find the roots. We can use the quadratic formula. So we say, okay, L is minus b, so that's 1, plus or minus the square root, b squared, 1, minus 4ac. So that'll become plus 4 over 2. Now, what do we end up with? Well, two possibilities. 1 plus square root of 5 over 2, or 1 minus square root of 5 over 2. Okay, We've mentioned before, I can't approach two different numbers. What have we found? Well, we said we know L satisfies a relationship. And among all the numbers that there are, because there are many numbers, there are two candidates. So we've now said, look, L has to be one of those two. But which one? Well, let's think about one thing that's we can say. Let's look at this one, because there's a minus here. Which is bigger, 1 or square root of 5? The answer is square root of 5 is bigger. So if you look at this one, this is a negative number. Now, can we rule it out? Well, think of what's happening here. We're starting at 1, and then what comes out, it's always going to be the square root of 1 plus something, at least 1, right? So that a sub n is always at least 1. So it's the square root of 1 plus something. So I can't end up with a negative value. So this one is out. And therefore, it must be that this is our answer. 1 plus the square root of 5 over 2. All right, great. So we can write that as, if we think about imagining going all the way down, this is square root of 1 plus 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 square root of 1 plus, and so forth and so on. So that's the conclusion. If you keep doing that, 1 plus square root of 5 over 2. Now, fun side note. This isn't just a random number. This is actually a number with some history. Do you recognize it? It is the golden ratio. It's denoted with phi. And so, what's interesting about the golden ratio? Well, the Greeks believed that the golden ratio was a ratio. Okay, so what are we taking a ratio of? The idea was if you took a rectangle and one side had length, say 1, and the other side had length phi, that this rectangle, this precise rectangle, is the most beautiful rectangle. At least that's what the Greeks believed. Now you might say, well, what makes it so beautiful? Well, the idea is it says, hey, if you cut off a little 1 by 1 square, then you have a little piece left over, and this rectangle is in the same proportions. So that's why they thought it was the most beautiful rectangle. Now you might wonder, were they right? Is it the most beautiful rectangle? And the answer is no. So somebody went out and they took a page and they just printed out lots and lots of random rectangles. And they would go around and did a survey. And they say, okay, please point to the best looking rectangle. Yeah, they did this. And they looked, and so people looked at the responses. And it turns out, nope, it wasn't the golden ratio. Oh, well, that's all right. It's still a nice looking rectangle. Don't get me wrong. It's just not the best looking rectangle. So, okay, well, on to more problems. More problems to do. Okay. So, let a0 equals 1 and a sub n equals n times a sub n minus 1. So, more recursive. We're going to do a lot of recursive ones today, but that's okay. I think recursive sequences tend to be fairly common when we see sequences. So it's good to get into the habit of understanding how they work. Find a simple expression for a sub n. And so I think when it says find a simple expression, it really just says keep going till you spot a pattern. So here, this is n equals 0, a0 equals 1. a1, well, okay, that's n equals 1. That's 1 times a0. Okay, well, according to the rule, that's 1 times 1. All right, a2. So that's n equals 2. According to the rule, that's 2 times a1, which is 2 times 1 times 1. a3, well, according to the rule, that's n equals 3, 3 times a2. All right, 3 times 2 times 1 times 1. a4, 4 times a3. Okay, 4 times 3 times 2 times 1 times 1. Do you see the pattern? Well, let's write down one more. So it would be 5 times the previous one, 5 times 4 times 3 times 2 times 1, and there's a times 1 on the end. So what's happening here? Well, we can spot something, right? We say, oh, I see what's happening. There's this 5 times 4 times 3 times 2 times 1. There's 4 times 3 times 2 times 1, 3 times 2 times 1 times 1, 2 times 1, 1. Those look like what we call factorials. Say, okay. So this, really, don't worry about the 1. That's 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 factorial. Aha! So we say perfect. So an is n factorial. And great. Good. Now, you might say, what about a0? Okay. All right, let's talk a little bit about a0. Why not? We have time. We're amongst friends. We can have this discussion. If we apply the rule, this would be a0 equals 0 factorial. And according to this, that should be 1. So, the question, does 0 factorial equal 1, and does it make sense? Now, one point of view says, wait, 0 factorial, wouldn't you start multiplying at 0, so you should get 0 out? But there's a different way to think about what's going on here, and I think it's important to understand that. How do we think of factorials? So if I think of 5 factorial, I start and I say, okay, 5 times 4 times 3 times 2 times 1, right? So at every stage, we start with whatever the current number is, and we keep going down by 1, and we stop when we hit 1. Now the problem is, at 0 factorial, we just don't even start. And so what's going on is 0 factorial, we don't multiply anything together. So really you can think of this as what we would call the empty product. Now, here's the question that we have to think about. If we multiply nothing, so in other words, that's what we mean by empty product, no multiplication happens, what number do we have? So before we do that, because I think people get uncomfortable with that answer, let's go to addition. Suppose we don't add anything, so we have an empty sum. Nothing is being added. What do you have? Now, I think a reasonable answer, and everyone agrees with this one, is 0. You didn't add anything, so you have to have 0. But what does 0 represent? 0 represents what's called the additive identity. In other words, if you add 0 to something, you get the original something. And so it's sort of like, in some sense, like a neutral number. Like, okay, look, it's that number where if nothing has happened, okay, that's where you should be at. So for addition, it's 0. For multiplication, what's the multiplicative identity? In other words, if you multiply anything by this nice number, you get back to where you started, the answer is 1. And so the convention says, look, an empty product where no multiplication occurs corresponds to the value of 1, because that's the multiplicative identity. And that's why we follow the convention that 0 factorial equals 1. All right, now that's sort of a reasoning. There's another reason why we do it. It's because it makes all the formulas really nice and elegant. And if it wasn't 0 factorial equals 1, we'd have to go through and redo all our formulas and say, and in the special case of 0, we do this. So 2 good reasons now. That's more than enough. We just really need 1 good reason to do something, right? Now we have 2. Ha. Mwahahaha. Okay. Our next one. Let B0 equal 0 and B1 equals 1. And B sub n is the sum of the previous 2. And the problem, all right, write down all the way up to 8. So this is a recursive, but notice it says, look, it's a little bit more interesting than before. Because it says, if I want to know my current term, I look at 1 and 2 back, right? Because if this is my current term, this minus 1 here says look at the really one right before. The minus 2 says look at the one 2 back. So I have to look at both the previous and 2 back. All right, no problem. So the problem, once you get going, it's actually pretty straightforward, right? So you say, okay, I just add the previous 2. 0 plus 1, 1. All right. Add the previous 2. 1 plus 1, 2. Add the previous 2. 1 plus 2, 3. Previous 2. 2 plus 3, 5. All right. Add the previous 2. 3 plus 5, 8. Add the previous 2. 5 plus 8, 13. Add the previous 2. 8 plus 13, 21. And of course you can keep going. And so those are the numbers all the way up through the B sub 8. Now, do you recognize these numbers? They're pretty famous. They actually have a name. These are called the Fibonacci numbers. And essentially, if you look, where do they come from? Well, Fibonacci, he was a mathematician. He wrote a book, Liber Abaci, which was basically algebra book. Well, even more than that, just arithmetic book. And the idea, he said, look, people used to do computations with Roman numerals. And of course, you rarely see Roman numerals. Well, you see them like super balls and things like that. But they're really hard to compute with. And it used to be that mathematicians were sort of this elite group that could carry out the complicated computations. And that, look, math was not for the masses. But there was a person, Leonardo da Pisa, who became known as Fibonacci, which means the son of Fibonacci. And he said, look, no, math is for everyone. And he introduced people to the Arabic number system. And he said, look, here's how it works. Here's how you can do things like add. Here's how you can do computations, multiply. You can do your own math. And once people realized, whoa, we could do our own math, the world got to be a better place. And dramatically, in a very short time, all of a sudden, people became wealthier, happier, life was good. They just needed more math in their life. And so in this book, Liber Abaci, there were exercises. And one of them basically related to the Fibonacci numbers, and it's similar to a problem that says, look, you're on an island, and there's some rabbits, and rabbits, they like to make more rabbits. And then the question was, okay, given that this is the number of rabbits is based off of how many were there the month before and 2 months before, okay, how many rabbits will there be after so many months? It really came down to this computation. Well, it turns out these numbers show up in a lot of interesting places and a lot of wonderful applications. And indeed, there's even a whole mathematical journal dedicated to their study. So just when you think, aha, we know everything there is to know about Fibonacci numbers, someone comes along and says, we can know a little bit more. And yeah, I even wrote a paper about Fibonacci numbers. Look, there's still so much to learn. Wow, life is good. All right, well, let's do one more. One final problem to finish this up, and I think this is a good one. Okay, let C0 equals 0, and C sub n is n plus C sub n minus 1. Find a simple expression for C sub n. Now, it feels similar to a problem we did a few back, where we had at one problem we said, oh, multiply. And we got the factorial. Big numbers, bah, 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 bah. They're huge. Factorial grows very quickly. So it says, no. Add. Okay. All right. So let's see. What can we do? All right. Well, let's see if we can spot a pattern. C0 equals 0. Okay, that's easy. So C1, so that's n equals 1. 1 plus C0. Well, that's 1 plus 0. Okay. All right, it's just 1. C2, well, that's 2 plus C1. So we can write that as 2 plus 1. Or if we want to, we could write that as 3. All right, how about C3? Well, okay, that's n equals 3. 3 plus C2. All right, and that would be 3 plus 2 plus 1, also known as 6. C4, okay, that's 4 plus C3. That's 4 plus 3 plus 2 plus 1, also known as 10. Okay. C5, okay, that's 5 plus C4, right? Because that's n equals 5. 5, C4. All right. So that's 5 plus 4 plus 3 plus 2 plus 1, 15. Okay, great. Now, we can see at least one of the patterns, right? And that pattern is Cn. See, look, at 5, we had 5 plus 4 plus 3 plus 2 plus 1. 4 plus 3 plus 2 plus 1. 3 plus 2 plus 1. So in general, it looks like n plus n minus 1 plus ... down to 1. Okay. That doesn't look like a simple expression. One of the things that, there's always the question, what do you mean by a simple expression? And that's actually more subtle than you might think. In some sense, the ... makes us say, it's not quite there yet. Because when you see a ... you really are saying there's a pattern and it's continuing. You're like, let's somehow find a way to compress that. Okay, so how can we do this? We will find a nice answer for it, but before we do, let's talk about what these are and see if we can't get a good handle on what it should be. So these are called the triangular numbers. And let me see if I can convince you about why this should be a triangular number. So let's start. We have a 1. I'm just going to do the very, very old-fashioned form of counting. And the very, very old-fashioned form of counting is just little stones, and you keep throwing them down. So I'm going to represent my dots here. So there's 1. And then the next thing will be 2. Okay. And then the next one will be 3. And the next one will be 4. And so forth and so on. And you can imagine we keep going for a while until we eventually end up with some number. Okay. So there are my dots, and however many dots there are, that's that number. Okay, so there's a 1, 2, down to n. All right, so how are we going to count? Now, this is a really fun, beautiful argument. And I just want to say before, don't panic if you're like, how did you come up with that? That's so beautiful. It just makes me want to cry because you get so emotional when you see it. But it's going to be fun. Okay, so here we go. I'm going to put some stones down to complete this. So I'm going to put one stone here. And then in the line above it, I'm just going to put 2 stones, right? Because if you went one line up above, there'd be another stone sitting right there, okay? And I'm just going to keep going. So I'm just filling in the stones, and when we do this, what will you see? Well, you probably, of course, if you engage in college humor, you say, oh my gosh, we're kind of stoned right now. But no, we don't do that kind of humor. That's lowbrow humor. We can be better than that. We have a lot of stones, and you can say, hey, I can really split them into 2 parts. And if I look, there's the same number of stones in each side. Okay, well that's great, because what have you done? Well, you really have 1 blue stone here, 2 blue stones in the line above, 3 in the line above, and up here you'll have n blue stones. So it's like you went and reversed it, so it's right? Okay. All right, now, great. So equal number. Now, the question is, okay, that's nice, but how many stones are there total? And in particular, we want to know how many stones there are here, and you see it forms this nice little triangle, and it's the reason we call it a triangular number. But triangle might be hard to count, but notice that once we've added these extra stones, what do we have? We have rectangle. We like rectangles because it's very easy to count. And in particular, we say, okay, the number of stones for the rectangle, well, you just have to count how many rows do you have? Well, 1 to n. How many rows across do you have? Well, there's n and 1 more. So n plus 1. And now we say, great. But remember, we don't want the rectangle. We want just the ones in this triangle, which is half of what we want. And so we come to our conclusion that the number of stones here, which is 1 plus 2 plus plus n, is equal to 1/2 n times n plus 1. Let's check that. Let's plug in 0. 1/2 times 0 times 1, 0. Plug in 1. 1/2 times 1 times 2, 1. Plug in 2. 1/2 times 2 times 3, 3. Let's skip to 5. 1/2 times 5 times 6. Well, that's going to become 5 times 3, 15. Now, legend has it, there was a very good mathematician who, when he was young, had a teacher who was just having not a great day. So the mathematician's name was Gauss. The teacher said, look, students, add up the numbers from 1 to 100 on their slates. So they had these little slates, kind of like little mini blackboards that they'd write and do their computations on. And so the teacher said, look, add up the numbers 1 to 100 and put it in when you're done. You bring it up to the front. And so the students started writing down 1 plus 2. Okay, that's 3. Add 3. That's 6. And Gauss just sat there and thought about it. And he realized, wait a second, there's got to be a better way, and came up with an argument. Legend has it. Who knows how much of this story is true, but it's a great story. Why should we let truth prevent us from sharing our great stories? Then he came up with a similar argument to this and did it in his head and said, if I want to add up the numbers from 1 to 100, it turns out that's the same as a half times 100 times 100 plus 1. Well, that's really 50 times 101, which is really 5,050. So, with writing nothing else down on the board, just wrote down 5,050, went up to the front of the class, and put the board down. And the customer wants to put it face down. At the end of the class, because the students eventually finished their work, the teacher started to look at the solutions, and of course was very annoyed that Gauss had not taken this assignment seriously, and was amazed that Gauss had the correct answer. That was the only thing. And more, he was the only person who had the correct answer, because all the other students had made mistakes, which of course it's almost inevitable if anybody asks you to add up 100 numbers that somewhere along the lines you'll make mistakes. So he went on to do great mathematics, but what is this moral of the story? Well, look for other ways to solve your problems. Don't just say, well, okay, let's just do it and be miserable. Math isn't about being miserable. Math is like, oh, you've got a problem here. Can we think about other ways to solve it? The answer may be no, not right now. But oftentimes, if you start thinking, there's some good solutions out there. All right, well, enough stories for now. Thanks for coming. Keep up the work, and I hope to see you again. Bye.